Fragility fracture of the pelvis, FFP, has increased rapidly related to osteoporosis. Romans and Hoffman classification system has provided a systematic understanding of fracture type of FFP. Romans type 3, especially type 3A, is more likely to be operated on due to external rotation of the ilium and worse mortality and mobility. However, the exact mechanism of FFP remains unclear. To clarify the injury mechanism of Romans 3A can be useful in the development of the prevention, new operation procedure, and understanding the risk factor. One of our Romans 3A cases fell laterally and with flexion and external rotation position when rising from a chair. We hypothesize that Romans 3A is caused by lateral compression and that hip limb position is involved. The purpose of this study is to simulate Romans 3A FFP using QCT-FEA. We use CT data from the patient with Romans 3A treated at our trauma center and created hem pelvis femur QCT-FEA model from the non-fracture side. On the software, we set the pelvic ring to be fully constrained in the center and the distal femur to be fully constrained except in the loading direction. We define the femur as an elastic material. Material properties were set based on previous studies. Considering Young and Burgess classification, we simulated lateral compression type and vertical shear type. As you can see, we have set the loading conditions. We applied 2000 Newton loads from these 4 points. In loading condition number 3, the hip limb positions were modeled with 15 degrees off from 0 to 90 degrees each and 3 rotation positions. First, as a qualitative study, we compared the distribution of compression failure elements and fracture images. Second, as a quantitative analysis of iliac fractures, we performed a force displacement analysis through the hip joint. We created 21 models, including 7 types of flexion and 3 types of rotation, and then applied a 3 mm force displacement axially along the femoral neck. In this analysis, we defined the sacrum and femur as elastic material. We measured the external constraint force and created a force displacement curve. We defined the peak value of the curve as the load value, at which fracture begin to occur, and then we compared it across models. These are the distribution maps of compression fracture elements. Compression failure elements are shown in white. In the models of iliac wing, hip rotation, and ischial tuberosity, the elements were distributed mainly in the sacrum. In contrast, in the hip flexion models, the compressive failure elements were distributed in the iliac wing, and the fracture morphologies were similar to Romans 3A. The next step is the strength analysis. The data is graphed for each rotation group. Peak values were lowest at the 45 degrees of flexion in the 0 degrees of rotation group. The external rotation group has the lowest peak value at 0 degrees of flexion, and the internal rotation group at 60 degrees of flexion. The lowest peak value among all models was 722 Newton for the internal rotation plus 60 degrees of flexion model. Our QCT-FEA has demonstrated that Lorenz type 3A FFP might be caused by lateral fall and associated with hip limb position. The direction of the fall was significantly associated with fracture type. Iliac fractures were more likely to occur in lateral fall patterns, particularly when the hip is in internal rotation and flexed at 60 degrees. We created QCT-FEA models of the hem pelvis to simulate FFP. Flexion models, especially 30 to 60 degrees flexion models, were similar to Lorenz type 3A. Lorenz type 3A is similar to Liangan-Burgess LC type 2. However, in Lorenz type 3A, the ilium is externally rotated, while in LC type 2, it is internally rotated. The mechanism of this difference is not clear, and no previous studies have simulated it. Our models was able to simulate external rotation of the iliac wing. In the analysis 2, we performed strength analysis focusing on the hip limb position. The minimum peak value was 722 Newton in the model of internal rotation and 60 degrees of flexion. In the mechanical study of the femur, fracture load was reported to be 3,400 Newton by mechanical test and 4,500 Newton by QCT-FEA. Although they are not simply comparable with our results, their average loading differs significantly from our study. Biomechanical studies around the hip joint have indicated that the rate of energy absorption into the femur may differ, depending on the direction and position of loading on the femur. Even in the pelvis, the energy absorption rate may differ depending on the loading position and direction, so-called anisotropy. In addition, based on our study, there may be some hip limb position such that pelvic fracture occurs earlier than in the femur. These are the limitations of our study: single case study, phantom-less analysis, hemipelvis analysis, considering only bone and joints, and the femur was set to elastic material. Conclusion: Lorenz type 3A FFP could be more easily caused by lateral force when the hip is in 60 degrees flexion with internal rotation. Thank you for listening.